Hello everyone, welcome to this session. Before starting today's session, let us see what we studied in the last class. If you recall, in the last class we discussed about orifice and mouthpiece. We started with the orifice. We defined orifice as a small opening provided in the side of the tank or at the bottom of the tank. A mouthpiece is a small tube whose length is equal to 2 to 3 times the diameter, and this short tube is connected to this orifice. I said this orifice and mouthpiece are used to measure the discharge. That's about the definition. Then we studied different types of orifices. I said you have a circular orifice, a rectangular orifice, trapezoidal orifice. Similarly, mouthpieces are also classified as circular orifice, then rectangular mouthpiece. When I was talking about mouthpiece, we discussed about external mouthpiece. If the mouthpiece is connected externally to an opening, then we call it as an external mouthpiece. If you connect the same tube inside the tank, then the mouthpiece behaves as an internal mouthpiece, and in that case Barrages mouthpiece is a popular one. That's about the different types of mouthpieces. We defined what is known as Vena Contracta. So we defined Vena Contracta is a point where the streamlines are parallel, the jet has a minimum cross sectional area, and the pressure at that point is atmospheric. So then we derived an equation for discharge through the orifice as well as mouthpiece. So while deriving, we showed that the coefficient of discharge for a mouthpiece is much higher than that of the orifice. So that's why these mouthpieces are preferable over orifice. Then we discussed about hydraulic coefficients. We discussed about 4 hydraulic coefficients: coefficient of discharge, coefficient of velocity, coefficient of contraction, and coefficient of resistance. If you recall, I said, so most of the time we use only the first 3, and the last one most of the time we use that when we talk about the pipe network. So we define this coefficient of discharge as a ratio of actual discharge to the theoretical discharge. The coefficient of velocity has actual velocity of the jet at Vena Contracta to the velocity of the jet at the orifice. Then we define this coefficient of contraction as the area of the jet at Vena Contracta to the area of the orifice or the mouthpiece. This is how we define these coefficients. Then we also showed a relation among these 3 hydraulic coefficients. We showed that this coefficient of discharge is equal to coefficient of velocity into coefficient of contraction. Then we solved couple of problems on this orifice and mouthpiece. This is what we discussed in the last class. So with this background, let us start today's class. So today I am going to talk about these notches and wears. So basically, if you recall, I said orifice and mouthpiece is based on Bernoulli's equation. Similarly, these notches and wears are also based on Bernoulli's equation, and these 2 are very important for a civil engineer. So as you progress further and further, what I mean to say is, when you come to 5th semester, when you come to 7th semester, when you talk about hydrology, when you talk about irrigation engineering, when you talk about hydraulic structures, you come across these notches and wears extensively. That's why these notches and wears are part of civil engineer's life. So that's why this topic is very important. Let us first define what is a notch, and let us see what is the difference between a notch and a wear. Then we will define what is the difference between a notch and a orifice. Basically, a notch is a device used for measuring the rate of flow of liquid through a small channel or a tank. Come on sir, you said orifice and mouthpiece is also a device used to measure the discharge. Yes, orifice and mouthpiece is also used to measure the discharge in a tank. Here this notch is a device used for the same thing in a channel or in a tank. Then what is the difference between a notch and a orifice? If you recall, we defined this orifice as an opening provided in the side of the tank or at the bottom of the tank. I said most of the time this orifice is provided in the side of the tank. If that is the case, if you recall the figure what I showed in the earlier lecture, I showed a bottom edge and a top edge. Okay. Now that is for a orifice. But if you look at this notch, okay, now this is a notch, a side view of the notch. Okay, I will show you the front view probably in the next slide. Now if you look at this, it has only the bottom edge, there is no top edge. That is, above this the fluid is flowing under atmospheric pressure. Okay. So in case of a notch there is no top edge, whereas in case of an orifice there is a top edge. Now the level corresponding to this bottom edge is called the sill level. Okay. I repeat, the level corresponding to this bottom edge is called the sill level, or it is also called crust level, or it is also called initial level. Why it is called initial level? Because remember, this acts as an obstruction. Now when there is a flow in this channel, okay, up to this level, this dotted line, there is no flow on the downstream side. This is upstream side, this is a downstream side. Now once the water level rises above this sill level or crust level, then water starts flowing over this notch or the weir. Okay. Since this is the reference line or the initial line, so with respect to which you are going to measure how much depth of water is flowing on the notch, that is why this is called the initial level. Now it is an opening in the side of a measuring tank or a reservoir such that the water level is always below the top edge of the opening. Okay, remember again I said there is no top edge in case of a notch. Now what is the difference between a notch and a weir? Remember, this is a plate, whether it will be a cast iron plate or an aluminum plate. Now look at this, this is the profile of the jet. Okay. Now this is the wall of the notch, and if this portion, okay, kindly concentrate on this. So this is the free jet and this is the wall of the notch. If I fill this portion with concrete or masonry, this acts as a solid wall, then this structure behaves as, or as this masonry structure is called as a weir. Okay. Again I repeat, weir and a notch is used to measure the discharge. Again, so what is the speciality of this weir? Usually whenever I want to raise the water level on the upstream side, again I repeat, this what I showed is a masonry structure, here is a weir. Now if I want to raise the water level above this weir, then we used to go for what is known as this weirs, or in some cases we talk about, when you come to 5th semester or when you come to 7th semester, you talk about what is known as barrages. Okay. Again, this is also used to measure the discharge and also raise the water level on the upstream side. Again I repeat, so here this is a plate. Okay. Whereas when I am talking about a weir, it is a masonry structure or a concrete structure. Now this masonry or concrete is placed between the free jet and the wall of the notch, then this structure behaves as a weir. Now remember, here if you recall, when I was talking about the orifices, so we classified these orifices based on the edge condition. This is a sharp edge, and if you recall, we also defined what is known as bell-mouthed entry. So I said whenever you have a sharp edge, the fluid in contact with the notch or the orifice is minimum, whereas if you talk about a bell-mouthed end, then the fluid will continuously in touch with the edge. Now if you look at this figure and this figure, now as the water flows over this masonry structure, so the fluid is in contact with the masonry structure right from the starting point to the ending point. If you come to this notch, here it is a sharp edge, so the area of contact is minimal, when I am talking about a sharp edge notch. I hope these things are clear. Now, look at this. This I said this is the free jet. So, in fluid mechanics, this free jet is called nappe, N-A-P-P-E. So, this nappe are free jet. This is what I said. The bottom edge of the opening is called sill level or crust level or initial level. Now, coming to the classification of notches. Now, notches are classified as according to shape of the opening. We have a rectangular notch, we have a triangular notch, you have a trapezoidal notch, you have a stepped notch, and finally you have what is known as a sutro notch. I didn't put that. I'll talk more about that at the fag end of this chapter. Again I repeat, based on the shape of the notch, we have a rectangular notch, triangular notch, trapezoidal notch, and stepped notch. Then this is very important. This is the first time we are introducing this terminologies. According to the effect of the sides on the nappe, we have notch with end contraction, notch without end contraction, or it is also called suppressed notch. We will see one by one. Now, this is a rectangular notch. Remember, this is a plate. In the plate, okay, at the center you cut a rectangle, then this behaves as a rectangular notch. This is a triangular notch. Look at this. This is a channel. So, in the channel we placed a triangular notch. Basically, take a plate, whether it is a mild steel plate or aluminum plate. At the center of this plate, you cut this V-notch shape or a triangular notch, then this becomes a triangular notch. Coming to a trapezoidal notch, again a mild steel plate or a cast iron pipe or plate or a aluminum plate, again you cut this plate in the form of a trapezium at the center, then this behaves as a trapezoidal notch. The one what you are seeing here is a stepped notch. Most of the time, if you go to your laboratory, you are going to see this rectangular notch, a triangular notch, very popular, and a trapezoidal notch. Very rarely you are going to see this stepped notch. Okay, so basically here you have different steps. Okay, so this type of notch is called stepped notch. This is very important. Now here I showed two channels. Okay, remember this is one end of the channel, this is another end of the channel. It is also called banks, B-A-N-K-S. I start introducing the terminologies which civil engineer is going to use from here afterwards. There are two banks. If you take any river or a channel, it has a left bank and a right bank. Okay, so these banks are nothing but the sides of the channel. Remember, here this is one bank, this is another bank. Similarly, I showed another channel. Okay, again the red line what I showed here is one bank, this is another bank. Now I introduce notches. For example, you talk about a rectangular notch, you talk about a trapezoidal notch. Now here if you see this and this, okay, now here my width of the channel is represented as B, whereas the length of the notch I provided is L. I repeat, the width of the channel is B and the length of the notch I provided is L. What it means basically, and this is the direction of flow. Now water, this is upstream side, this is the downstream side, water flows over this notch. Now in this case, in the first case, my L is less than B. I repeat, in this case the length of the notch is less than the width of the channel. Okay, this is the first case. So this is called a end contraction notch. Come to the other side. Here this is the length of the, this is the width of the channel and my length of the notch is equal to L. In other words, this B is equal to L in this case. Okay, it is called the suppressed notch. Let us see why it is called notch with end contraction. Why it is called suppressed notch? Now, to answer that question, kindly concentrate on the blue lines what I showed here. Now, if you talk about, I said this is the length of the notch. Okay. Now, you have here the width of the channel is B. Remember, the fluid particles or the water particles moving close to this channel. So, it starts moving towards the downstream side. Now, when it comes to this, so they change the path, and finally, since this is an opening, they start moving towards that, and again after passing through, again they divert again. Okay. So, in this case, since the length of the flow is not equal to the width of the channel, we talk about what is known as end contractions. I repeat, when my length of the notch is not equal to the bed of the channel, then we have end contractions. Okay. Come to the other side. Here we set this B is equal to L. My length of the notch is equal to B. Here, if you look at this green lines, what I mentioned here, so there is no deviation from the upstream side to the downstream side. These fluid layers or fluid particles slide smoothly over the notch. Okay. So, in this case, since the fluid is not taking any diversion and it flows over the entire notch, this we call it as what is known as suppressed notch. So, if L is less than B, we have end contractions. If L is equal to B, we do not have end contractions. That type of notch is called suppressed notch. With that basics, let us derive an equation for this discharge through a rectangular notch. Okay. Now, in order to derive an equation for this discharge through a rectangular notch, I consider a sharp edge rectangular notch. Now, this is a side view. If I stand here and if I observe this, I repeat, so this is a side view of the rectangular notch. If I stand here, if I observe this portion look like this. Okay. So, at the center you have this opening, and this opening, since this is in the form of a rectangle, this behaves as a rectangular notch. Here, the length of the notch I represent this as capital L. Recall that now this is your initial level, crust level or sill level. I repeat, this is your initial level or sill level or crust level. What it means? So, up to this level there is no discharge over the notch. Once the water level rises above this level, then the excess water starts flowing over the notch. Since this is the reference point, okay, we are measuring the head or the depth of water above this notch with respect to this line. That is why it is called initial level. Now, here I showed this maximum depth, that is the maximum depth of water you are allowing in the channel or above the notch, that I represent this as capital H. Okay. Now, remember, my head or the depth of water on the channel varies from, here it is 0 and here it is capital H. I repeat, the head over the notch varies from 0 at the sill level to a maximum value of capital H. Okay. Now, with these basics, so let us consider a small strip sheet of water at a depth h from the free surface. You must be very careful with this notation. Here I represent this as small h and here I represent this as capital H. Capital H is the total depth of water above the notch, whereas at any given depth from the free surface, if I consider a small strip, that depth from the free surface, I represent this as small h. Hope it is clear. This is what I mentioned here. Let h, head of water over the crust, L is the length of the notch. Consider an elementary horizontal strip of water of thickness dh and length at a depth h from the free surface. Let me go back to this figure. Now, this length, remember, this is a rectangle. You take any point from capital H to 0, the profile remains the same. it won't change. So the length is L and the thickness I take it as dH at a depth h from the free surface. That's what I mentioned here. Now if that is the case, what is the area of the strip? Thickness is dH, length is L. Therefore, if I call this as dA, dA is equal to L into dH. Kindly recall, in the last class we derived an equation for this theoretical velocity. What is that equation? V is equal to root of 2gh. What is this equation called? This is called Torricelli's equation. Okay. So by Torricelli's equation, the theoretical velocity of water flowing through the strip is given by, so V theoretical is equal to root of 2gh. You know the area, you know the velocity. Now if you know the area and if you know the velocity, you can easily calculate the discharge. So what is the equation I am going to use? Q is equal to A into V. So in this case, since you are talking about the discharge through a small strip, I take this discharge as dq. Now dq is equal to area of the strip into velocity of water through the strip, that is LDH into root of 2gh. Remember, I said this is the theoretical velocity. Now if you recall, if I multiplied by this theoretical velocity, theoretical discharge by this coefficient of discharge, which is always less than or equal to 1, I am going to get the actual discharge. I repeat, if you multiply this theoretical discharge by the coefficient of discharge, you are going to get the actual discharge. Now in this case, this actual discharge is equal to this coefficient of discharge into this theoretical discharge, that is given by, so area of the strip LDH into root of 2gh. I hope this is clear. Now remember, here this entire depth from 0 to h, I divide this entire depth into number of small strips. I am going to find the discharge through each and every strip. If I sum up this discharge from 0 to capital H, I am going to get the total discharge over the entire depth of rectangular notch. I repeat, so here, so I consider a small strip of thickness dH. I found out the discharge through this strip. Similarly, if I divide this entire depth of water into a number of small strips and finding the discharge through each and every strip, and if I go on summing up from sill level to the maximum value of H, I am going to get the discharge for the entire rectangular section and over the entire depth of flow capital H. That is what we are going to do in the next step. Look at this. The total discharge over the whole notch may be found by integrating the above equation within the limits 0 and h. At sill level or initial level, my value of small h is equal to 0 and it reaches a maximum value of capital H at the top, at the free surface. So what I mentioned here, again I repeat, you are dividing this entire depth of 0 to h into number of small strips. Finding the area and finding the discharge in each and every strip. If you just go on summing the discharges from 0 level to a maximum level, you are going to get the total discharge over the entire notch. So that is what we did in this case, we are doing in this case. Now earlier it is dq. If you integrate that, you are going to get this total discharge. Total discharge is equal to, so integration of the lower limit is 0 and the maximum limit is capital H. So with the limit 0 and h, CD into L into root of 2gh into dH. Now if you simplify this, remember the coefficient of discharge is a constant value. The length of the notch L is constant. It won't change from trial to trial. Okay, once you fabricate the plate, it is fixed, and root 2g is a constant. So that is why, so take out this CD L root 2g out of this integral sign, you are going to get this 0 to h integral root of h into dH. If you integrate this equation and submitting the limits, lower limit and upper limit, and if you solve it, you are going to get this equation Q is equal to 2/3 CD L root 2G into H raised to 3 by 2. In general, this Q is equal to 2/3 CD root 2G L H raised to 3 by 2. Okay. This is what I mentioned here. Now, this is the discharge equation for a rectangular notch. Okay. Kindly recall at the beginning of this class, we said there are two types of notches. One is notch with end contraction, notch without end contraction, or notch without end contraction is also called suppressed notch. The equation what we derived just now holds good for a suppressed notch. What is a suppressed notch? If the length of the notch is equal to width of the channel, then we call it as a suppressed notch or notch without end contraction. If my length of the notch is less than the width of the channel, then it will not be a suppressed notch. It is called notch with end contractions. The equation, this Q is equal to 2/3 CD root 2G L H raised to 3 by 2 holds good for a suppressed notch. But where for a end contraction, I said whenever you have a end contraction, the crust length is not equal to the width of the channel. If you look at this equation here, in this case when I am talking about a suppressed notch, my B is equal to L. But if you have an end contraction, naturally my L will be less than B. In that case, discharge will be less. Okay. Now, according to J.B. Francis, the decrease in crust length depends only on head, and for each end contraction, the crust length reduction is equal to H by 10 or is equal to 0.1 H. Very important. Now, let us not get into the details of how you are going to derive this or how on what basis you are going to derive this and all. Now, if you know this will be more than enough. According to J.B. Francis, the decrease in crust length depends only on head, and for each end contraction, the crust length reduction is equal to H by 10 or 0.1 H. Why it is so? If you look at this equation, 2/3 is constant, CD is constant, L is constant, root 2G is constant. What is a variable? Q is directly proportional to H. Q is directly proportional to H. Now, based on that, he said, so for each end contraction, the crust, the effect will be 0.1 H. Then if this is the case, how we account for a discharge equation for a end contraction or a notch with end contraction? Now, if there are n end contractions, then the equation, this equation is modified as Q is equal to 2/3 CD root 2G L minus 0.1 NH. Why? Because this is the one which affects the discharge. So, L minus 0.1 NH into H raised to 3 by 2. Now, here for a rectangular notch, okay, so there are two end contractions, one on this side, one on this side. Therefore, my value of n is equal to 2. Now, if you substitute 2 here, then for a rectangular notch, so the equation becomes Q is equal to 2/3 CD root 2G L minus 0.2 H into H raised to 3 by 2. Now, you have two equations. This is one equation, this is another equation. This equation holds good for a suppressed notch. This equation holds good for a notch with end contractions. The next question, sir, in the examination, which equation we are supposed to refer? In the equation, in the problem, if they don't mention about the end contractions, kindly refer to this equation. If they talk about the end contractions, kindly refer to this equation. This is the thing you need to keep it in mind. Okay, notch without end contraction, notch with end contraction. Okay, now this is very, very important. The general one, L minus 0.1 H into H raised to 3 by 2. Okay, I hope these things are clear. Then you have, just now we saw, in case of a end contraction, we introduce L minus 0.1 NH. for a notch with a end contraction. So, in case of a suppressed notch, we do not have any modification of the original equation what we derived. But there are a couple of issues with this suppressed notch or notch without end contractions. So, there we are talking about what is known as ventilation of notches or wears. In order to explain this concept, okay, so look at this. This is a channel, okay, this is one bank, this is another bank. So, in between these two banks, okay, there is, I provided a wear or a notch. Okay. So, look at this, I mentioned here is B is equal to L. My length of the notch is equal to the width of the channel. Okay. So, typically, so according to our definition, this is a suppressed notch. There are no end contractions. Water comes, slides smoothly over the notch or a wear. Now, so what is the problem in this case? Okay. Kindly refer to the first case here. Now, this is the upstream side, this is the downstream side. I showed the arrow like this. Q is the discharge. Now, remember, till now we studied that you have a sill level or a initial level. Presume that this is the upstream side, this is the downstream side. Now, up to this sill level, there is no discharge. Okay. Remember, this is one bank, this is another bank. You have one wall here, you have another wall. In between this wall, you put this notch. Now, water starts coming from the upstream side. So, here, so up to this acts as an obstruction. Up to this sill level or crust level, there is no discharge. Come to the downstream side. Here, atmospheric, since there is no discharge, atmospheric air freely circulates here. Remember, there is a wall, there is a bank here, there is a bank here. In between the bank, you are going to put this notch. Okay. So, here I said atmospheric air freely circulates here. Once this water starts flowing over this notch, once the water level rises above the initial level, the excess water starts flowing over the notch. When it happens, some amount of air is trapped between the jet and the wall of the notch. I repeat, when the water starts flowing over the notch, okay, some amount of air is trapped between the jet and the wall. So, why it is trapped? Remember, there is a wall here, there is a wall here. This trapped air, so there is no passage for this trapped air to escape. So, that is what I showed here. Okay. Now, this is the notch. When the water flows, overflows, the overflow on this, there is some air trapped between these two walls. Since this is one wall, this is another wall, this air do not have any passage to escape out. So, what happens? So, kindly refer to this and this. Now, here the flowing water, so this carries this trapped air gradually. So, during this process what happens? Initially, when there is no flow over this notch, the pressure of this air is atmospheric. I repeat, when there is no flow of water over this notch, the pressure of air present on the downstream side of the notch is atmospheric. So, once the air is trapped here, the trapped air is carried away by this flowing water gradually. The pressure of this air gradually reduces. Earlier at the beginning it is atmospheric. Over a period of time, this atmospheric pressure gradually reduces. So, during this process, so due to this reduction in the pressure, this air, it sucks the jet towards the wall. Okay. Now, that type of nappe or free jet, we call it as what is known as depressed nappe. That is, this negative pressure or drop in pressure of air, it tries to suck the jet towards the wall of the notch. That we call it as what is known as suppressed nappe. Now, if this process continues, okay, at one given point of time, this complete free jet of water almost sticks to the wall of the notch. Okay, that type of nappe we call it as what is known as clinging nappe. Again I repeat, in case of a notch without end contractions, so whenever there is a flow, there is some air trapped between the notch and the free jet. So the pressure of this air at the beginning is atmospheric. This entrapped air is carried away by the flowing water gradually. During this process, the pressure of this air gradually reduces from atmospheric pressure to negative pressure. So during this process, this entrapped air, it tries to suck the jet towards the wall. The first stage in that case is called depressed nappe. If this process continues, at one given stage, the jet almost sticks to the wall of the jet. So that we call it as what is known as clinging nappe. Now, clinging nappes are not desirable. Why? Now, before explaining that, so refer to this. Now, this is a free jet. Remember, in this case, so presume that there is no air entrapped here. Whatever the jet that is flowing over the notch, it will be in the form of a free jet. Now, we expect the same type of jet profile here and here. Now, just now I said, so this is called clinging nappe and this is not desirable. Kindly recall the discharge equation. Q is equal to 2/3 CD root 2G LH raised to 3 by 2. Okay. Now, in this case, when there is a clinging nappe, the discharge flowing over the notch is I, whereas the depth over the notch is less. Okay. So, what happened to that? If you look at this equation, Q is I. Now, remember Q is directly proportional to H. Now, here suppose if the value of H is less, then whatever the discharge we are going to calculate using this equation will not match with the actual discharge that is flowing over the notch. I repeat, whenever there is a clinging nappe, the head over the notch will be less, whereas the discharge flowing over the notch is very high. In that case, if I use this equation, if I calculate the discharge, this discharge will not match with the actual discharge that is flowing over the notch. That is why clinging nappes are not desirable. I hope it is clear. This is what I mentioned here. In case of a suppressed notch, the free nappe emerging from the notch is in contact with the sides of the channel. On account of this, air is trapped between the notch and the nappe or the free jet. This air is gradually carried away by the flowing water. At the same time, the pressure of entrapped air reduces from atmospheric to suction pressure. Due to this, the nappe is drawn towards the notch. This nappe is called the depressed nappe. If this process continues, at one stage, the nappe clings to the wall of the notch. This nappe is called the clinging nappe. This is not desirable because it draws more water and thus the actual discharge for a given head over the notch will not match. In order to avoid that, usually how we are going to avoid that? So, go back to this. So, I said this is one wall, this is another wall. There are two ways of avoiding this clinging nappe. One is, if you provide, there is a vertical wall. In this vertical wall, at regular intervals, if you provide holes, the trapped air will automatically escape into the atmosphere. That is one way of avoiding the clinging nappe. Again I repeat, this is one bank, this is another bank. So, in between you have a notch. So, on the downstream side, if you provide at a random holes or vents, the trapped air will automatically escape into atmosphere, or atmospheric air will freely enter into the space between the notch and the jet. That is one way of avoiding this clinging nappe. Another way of avoiding the clinging nappe is, at the beginning of this class, we define this wear. So, how we define this wear? So, it is a concrete structure. So, this is the notch, over this you have a free profile. So, between this free profile and this notch, if you fill this portion with concrete or masonry, that structure behaves as a where. Now, if you provide this portion with concrete or masonry, so there is no place for air to be trapped. Okay, this is how you are going to avoid this clinging nappe. I repeat, providing vent holes in the walls, that is one way of avoiding clinging nappe. The other one is providing a wear on the concrete structure between the notch and the free jet. Okay. Now, let us start with a simple example on this rectangular notch. Now, Q is equal to 2/3 CD root 2G L H raised to 3/2. This is the equation we derived for a notch without end contractions. Based on that, let us solve a simple problem. Let us read the problem. A rectangular notch 0.5 meter wide has constant head of 400 mm. Find the discharge over the notch in liters per second if the coefficient of discharge for the notch is 0.62. A straightforward question. First, let us note down what are the data that is given in the problem. Length of the notch is given. Okay, here he used the B, let us not bother about that, put this as capital L. L is equal to 0.5 meter. What is the maximum height of water? Maximum height of water, capital H, is equal to 400 mm. So, that will be 0.4 meter. Coefficient of discharge 0.62 given in the problem. Consider the discharge equation. Q is equal to 2/3 CD root 2G L H raised to 3/2. Now, what is the data given in the problem? 2/3 is constant, CD is 0.62 and L is 0.5, root 2G is constant and H is 0.4. All the data given in the is given in the problem. Kindly substitute these values and find the value of Q, which is in meter cube per second. This is 0.231 meter cube per second. So, remember, so 1 meter cube is equal to 1000 liters. Therefore, if you multiply this by 1000, you are going to get this as 231 liters per second. A very simple example to give a flavor of this discharge over the rectangular notch. Let us see another case. Read this. A rectangular notch has a discharge of 21.5 cubic meter per minute. When the head of water is of the length of the notch. Find the length of the notch. Assume CD is equal to 0.6. Now, Q is equal to 21.5 meter cube per minute. You must be very careful here. This is 21.5 cubic meter per minute. Kindly convert this into cubic meter per second. If you do this, you are going to get, remember, 1 minute is equal to 60 seconds. Therefore, this becomes 0.358 meter cube per second. What is the head? So, here, so the head is equal to length divided by 2. Look at this, when the head of water is of the length of the notch. Assume the length of the notch is equal to L. Then your capital H is equal to L divided by 2, or it is equal to 0.5 L or B. Coefficient of discharge is 0.6. Now, consider the discharge equation. Q is equal to 2/3 CD root 2G L H raised to 3/2. Okay. Now, Q is given. You converted that into meter cube per second. 0.358 meter cube per second. 2/3 is constant. CD is constant 0.6, that is given in the problem. L, so not known. You need to find the value of L. Root 2G is constant, but you remember this value of H is equal to L by 2. So, L by 2 raised to 3/2. Now, if you simplify this, there is only one unknown B or L. If you simplify this, you are going to get the value of L is equal to 0.8 meter. Okay. That's about rectangular notch. You know, this a very simple notch, Most of the time we see this rectangular notch in the fields. The next most popular one is the triangular notch. This triangular notch is also called V notch. If you go to laboratory, most of the time you are going to see this V notches. V notches are very popular. Why it is called V notch? This will be in the form of a V. A triangular notch is in the form of a V, that's why it is called a V notch. Now this V notch is preferred over other notches. Kindly recall. So we said we have a rectangular notch, V notch, trapezoidal notch and step notch, sutro notch and so on and so forth. These triangular notches are very popular in civil engineering domain. Let us see why these triangular notches are very popular. So probably once we derive the equation. Okay. So this, in order to derive a discharge equation for this triangular notch or a V notch, I consider a V notch. Okay. Now so here this is the sill level or the crust level or the initial level. Now remember, this is the maximum depth of water we can allow in the channel. Then my depth head is equal to capital H. Now here I represent this value of this angle as theta. This angle we call it as what is known as apex angle. Now if I cut this triangle into two equal parts, I repeat, if I cut this into two equal parts and if I take one triangle, this look like this. Remember, this whole angle is theta, half of that is theta by 2. This whole vertical head is capital H. Now if you consider a small strip of thickness dh at a depth small h from the free surface, I repeat, in order to derive an equation, discharge equation for a V notch, consider a small strip of thickness dh at a depth h from the free surface. Remember, if you recall, in the earlier case I have a rectangular notch, the length of this notch is equal to L, therefore naturally the length of the strip is also equal to L. But if you look at this, here the length of the strip, if you consider the length of the strip at this point, if I call this as x, suppose if you take another strip here, if you call this as y, this is not equal to this. In other words, this length of the strip varies from depth to depth. So the first condition in this case is to identify, find the value of x. How to find the value of x? So that we will discuss in the next class. So let me recap what we studied in this class. We started with the definition of notch. We defined a notch, we defined a wear, we differentiated between the notch, wear and a orifice. We studied the different types of notches. Then we derived an equation for this rectangular notch. We solved one or two simple problems on rectangular notch. Then we started with this triangular notch. So we will continue this in the next class. Thank you.